Let me first briefly go over a few recent examples where our proposed techniques are successfully applied. For example, they are used to design a guidance and control algorithm to explore interstellar objects, ISOs, passing through a solar system on an unbounded hyperbolic trajectory about the Sun under the large state uncertainty and high velocity challenges. Its performance is also demonstrated on our thruster-based spacecraft simulator called MSTAR, and this is a case where I use them for intelligently controlling multiple UAVs in a distributed manner, robustly against external disturbances. They are commanded to move to randomized and high conflict target positions optimally, and by solving a highly nonlinear motion planning and feedback control problem in real time. As the next generation research objectives have become more complicated and large scale, the guidance, navigation, and control problems can easily become computationally or theoretically intractable for conventional nonlinear control, which has led to the emergence of learning-based control. So the purpose of my research is to step back and provide formal ways to enjoy the mathematical guarantees of nonlinear control theory, even with the use of learning-based autonomous control techniques, so we can accomplish the next generation tasks safely, robustly, adaptively, and intelligently in real time. Our work is summarized as an invited tutorial paper in the annual Reviews in Control and is featured at the IEEE CDC tutorial session. You can find the details with this QR code. But this is not to argue that our work will replace all the conventional nonlinear ZNC methods with learning-based methods, but to provide formal ways to determine whether or not we need machine learning in a given problem setting, so we can build truly autonomous systems without relying on a black box AI and machine learning approach. I will revisit this figure later, but we established stochastic contraction theory with the supermerging analysis to develop learning-based nonlinear feedback control, adaptive control, state estimation and motion planning, and neural network-based system identification and control, all with formal guarantees. And these are the papers cited here and to be cited in this presentation. Ideally, we want AIs or autonomous systems to work with a very high-level command and perform highly autonomous operations with any objectives, just like humans. This is to build autonomous aerospace and robotic systems to turn our imagination into reality in place of humans, but regardless of humans' inherent constraints. I aim to augment such truly autonomous systems with formal guarantees so we can build truly robust and adaptive autonomous systems that work in whatever dynamics and environments. One of the key challenges here is to deal with the nonlinearity of the dynamics. For example, the multi-agent guidance, navigation, and control of multiple spacecraft, where the picture is the one we have at Caltech, is a typical highly nonlinear problem in the field of aerospace. In the field of robotics, we have many highly under-actuated nonlinear dynamical systems, including swarms of UAVs with possible loader failures, or our bipedal robot with thrusters called Leo, which can walk, fly, skateboard, and slackline. In the near future, these nonlinear dynamics are expected to become much more complex and large scale. For example, in the case of flying and ground robots for fully autonomous disaster response, or more generally, in establishing any autonomous aerospace systems or exploring deep space purely to find something new but without even knowing what to do, where to go, or how to achieve it. Another challenge here is that the agents are supposed to perform autonomous operations in extreme environments, for example, on land with rocky and cluttered terrain, or in water, or in deep sea with challenging navigation conditions. or in the air with unexpected aerodynamics interactions and disturbances, or in deep space with outgassing targets under low state uncertainty and with spacecraft navigated just by its vision, as in our project of interstellar object exploration. These extreme environments always involve unexpected and possibly severe disturbances and uncertainties, which could be due to the unknown parts of the nonlinear dynamics and environments, human interactions, potential failures in the system, and adversarial attacks from other agents with opposing objectives. My research vision here is to establish a unified autonomous decision-making, design, and operation framework that work for all of these challenging scenarios with formal mathematical guarantees. Now let me talk about my work on contraction theory for providing formal guarantees for learning-based autonomous control. When I say formal guarantees, there are four types of guarantees I have in mind, although we plan to consider broader and more general types of guarantees in my future work. Our autonomous systems is required to be robust and adaptive to disturbances and uncertainties, and to stay in a safe region and achieve tasks optimally in some sense and in real time, even with the agent's limited computational capacity. We propose to get these guarantees by designing what is called an optimal differential Lyapunov function for general nonlinear systems. Before going into details, let me briefly review the concept of a Lyapunov function. Roughly speaking, Lyapunov theory aims to find a positive scalar function B that decreases along given nonlinear dynamics for the sake of stability, which is challenging in general. Instead, we use what is called contraction theory, based on differential dynamics and differential Lyapunov function, which studies incremental stability, so we can use linear time varying or LTB systems type analysis even in nonlinear problem settings. This property will be useful to easily obtain the formal guarantees, as we will see soon. I will first talk about the formal guarantees using stochastic contraction theory, assuming that we have a Lyapunov function or a contraction metric. I will then talk about how to find a Lyapunov function or a contraction metric optimally for general nonlinear systems. I will present how we can use it with machine learning for the real-time performance guarantees, and with online learning for actively using online information of real-world environments for improved performance guarantees. I will have to introduce some equations and mathematics for this purpose, but please note that I will try to give you high-level ideas of our work rather than focusing on the rigorous details on mathematics behind them. Let's start with the first part. Let me consider a nonlinear system with bounded disturbance and with unbounded stochastic disturbance modeled as the Gaussian white noise. One benefit of contraction theory based on differential dynamics is the use of this quadratic Lyapunov function for simplified but generalized robustness analysis. From now on, I assume these conditions for the existence and the uniqueness of the solution. Also, we can consider other types of stochastic disturbance, like shot noise for impulsive disturbance in uncertainty, like this one. In incremental analysis of contraction theory, we parameterize the system by mu to have perturbed and unperturbed system solution trajectories when mu equals to 1 and 0. Since the system is stochastic, we consider the weak infinitesimal operator instead of the time derivative for analyzing the time evolution. These equations are just for getting the decreasing condition for V, as we saw earlier in this figure. Let me derive a condition on M to make our nonlinear system contracting or our Lyapunov function decreasing. I have to omit some details, but after some algebra with these conditions, we end up with this scalar inequality, which implies that we need this matrix inequality for robustness because m bar times c is a term due to external disturbance and uncertainty. This condition is called a contraction condition. And finally, we get a decreasing condition of V with a constant for showing robustness as desired. Stochastic contraction now results in exponential boundedness of the perturbed solution trajectories with respect to unperturbed trajectories. One distinct feature of contraction is that any pair of unperturbed system trajectories converges to a single trajectory regardless of our initial conditions. This property is called incremental stability to distinguish it from traditional notions of stability, as I mentioned earlier. The main idea of contraction theory for learning-based control is that the disturbance term in the previous robust contraction theorem can be viewed as a learning error term in several learning-based control problems. Let us consider the problem of system identification as a simple example, where f true is an unknown nonlinear function for an ideal solution trajectory to be modeled by a contracting learned model FL. We can always decompose the system into a contracting part and the learning error part, and the latter part can be regarded as an external disturbance. The robust contraction theorem then guarantees that the distance between the trajectories of the learned model and the unknown ideal system model is exponentially bounded like this. And this is a robustness guarantee we can get as a result of stochastic contraction theory. Here, achieving tasks means that we can realize a learned solution trajectory close enough to the ideal solution with whatever ideal properties, even when the system does not have access to it. Due to various reasons, due to external disturbances and uncertainties, or problem nonlinearity or complexity, or agents' limited computational capacities. I will talk about the adaptation part later in this presentation. Also, we can easily get probabilistic bound on the tracking error with respect to the ideal solution at time t using Markov's and Lyapunov's inequalities. However, when using learning in safety critical situations, we often need to guarantee that the tracking error with respect to the ideal solution will not exceed a given safety critical distance for all time t, not just at the single time instant, as shown here. Unfortunately, the Lyapunov-like function cannot be used for this purpose because it's not a supermerging under the presence of external disturbance, uncertainty, or learning errors, which could lead to a positive differential of the Lyapunov function B. Instead, we can come up with a non-negative function W, which is supermerging L for a finite time interval. Anyways, what's important here is not the mathematical details, but that we can get the probabilistic bound now for all time until Tf using this supermerging L function. Although the time interval is finite, this bound gives the probability that the tracking error will not exceed the critical distance, the safety critical distance for all time until Tf instead of just a single time instant. And this is just one type of the safety guarantees that we can get as a result of stochastic contraction theory with the same reasoning as in the case of the robustness guarantee. More importantly, as long as we can get a Lyapunov function, we can use many tools of stochastic control theory to get powerful guarantees, including but not limited to these two robustness and safety guarantees. Let me additionally go over some other useful properties of contraction theory for those familiar with Lyapunov theory. Contraction theory uses a differential Lyapunov function that is always a quadratic function of the differential state delta x, unlike Lyapunov theory where v could be any function of the state x. It characterizes a necessary and sufficient condition for incremental exponential convergence of the multiple nonlinear system trajectories to one single trajectory. Its differential nature simplifies conventional stability analysis by its extensive use of exponential stability, as in linear systems where we cannot distinguish exponential stability from asymptotic stability. And you can find more details on the tutorial paper at the bottom. However, the results presented so far assumes the existence of a contraction metric, which is challenging to find for general nonlinear systems. So the next part of my presentation covers a convex optimization approach to design a contraction metric that makes the nonlinear system contracting. And this is the second part of the technical details of my work. Before going into details, let me clarify the categories of each control method I will talk about. We have nonlinear feedback control, state estimation, motion planning for target trajectory generation, and adaptive control and system identification for model uncertainty quantification. Let me start with the feedback control. We now consider a control affine nonlinear system with external disturbances, where XD/UD represents a target trajectory to be tracked by a contracting feedback control policy. We designed the controller U with a contraction condition for this nonlinear system, as discussed earlier. Please note that the nonlinearity is captured through a nonlinear matrix function A in order to allow linear systems type analysis even for such a nonlinear problem setting. Anyway, what's important here is not the mathematical details, but that the contraction condition, again, guarantees that the distance between the target trajectory xd and the control trajectory x is exponentially bounded like this as a result of stochastic contraction theory. The term C1 of M appears due to the presence of external disturbance, and it remains even as t goes to infinity. The method of CP-STEM is for finding the contraction metric M that minimizes this term for the sake of optimal disturbance attenuation. I will skip the details, but introducing these new decision variables enables expressing the nonlinear problem as a convex optimization problem. Let me explain this part a little bit more clearly. By looking at this figure, we can see that this optimization problem can be equivalently reformulated to this problem, which is called an epigraph form of optimization in the context of optimization theory. Using Show's complement lemma for this constraint, we finally get an optimization problem with a linear matrix inequality constraint. As a result, we have this optimization problem for finding an optimal contraction metric, where the contraction constraint and the objective function are now all convex, which means that we have a global solution. As a quick summary, this is the optimization problem for minimizing the steady state tracking error for optimal disturbance attenuation subject to the convex contraction condition. Again, we proved that this convex optimization problem is mathematically equivalent to the original nonlinear optimization problem of minimizing the bound. And this is the one type of the optimality guarantees of our contraction metric and Lyapunov function we can get on top of the robustness and the safety guarantees. Since the differential dynamics used in contraction theory can be viewed as a linear time-varying system, we have a similar control and estimation duality even for such a nonlinear problem setting. We can utilize such duality to design a state estimation counterpart of the CV stem control. As a result, we have optimal feedback control and state estimation frameworks for general nonlinear systems. Now we have a computationally efficient convex optimization based scheme of designing a contraction metric, which gives an optimal V-apnea function for a given nonlinear system. However, solving the optimization at each time instant could still be unrealistic for highly autonomous tasks for systems with limited computational capacity. We can therefore use machine learning for designing a contraction metric, and the contraction theory still provides some formal guarantees. And this is the third part of the technical details of our work. The idea is very straightforward. If we consider a time-independent contraction metric just for simplicity, we first solve the convex optimization to sample the optimal contraction metric for robust nonlinear control and state estimation synthesis. And once we get enough samples, we model the data by a spectrally normalized deep neural network. We can easily imitate the optimization because the problem is convex and thus has a global solution. These figures visually summarize this framework called neural contraction metric, or NCM. The major benefit of the NCM control and estimation techniques is that they can compute a near optimal control input or estimated state with one neural network evaluation, which is computationally efficient, while dealing with complex and large-scale nonlinear systems that conventional nonlinear control theoretical approaches could fail to handle. The major advantage of contraction theory is that we have the stability and robustness guarantees even for these learning-based control schemes. As we saw earlier, U star obtained by the convex approach can be computationally expensive as it involves solving optimization at each time instant. Therefore, we approximate U star by a spectrally normalized neural network for the sake of its real-time implementation. If we apply the NCM control to the system, we can always decompose it into the contracting system part and the learning error part, and we can then view the learning error part as external disturbance in order to apply contraction theory. The robust contraction theorem then guarantees that the distance between the target trajectory and the trajectory with the computationally cheap NCM control is exponentially bounded as desired, which means we still have the robustness guarantee of stochastic contraction theory even with the use of learning. By constructing a non-negative supermartingale function, we can still get these probabilistic bounds as we saw earlier, which means we still have the safety and stability guarantees of stochastic contraction theory. One remaining question would be how we can actually bound the learning error in the first place. Let's take a look at the case where we use the spectrally normalized deep neural network as an example. Let's consider the problem of modeling a function U star by UL, assuming that U star is Lipschitz. The strength of the spectrally normalized deep neural network is that it is Lipschitz by design, meaning that if the distance between the training and test data, theta and eta is finite, then the distance between UL of theta and UL of eta is also finite. These properties will guarantee that the learning error, indicated by epsilon LU, is indeed bounded. This also implies that we can still enjoy the CV stem type optimality we had in designing a contraction metric by convex optimization because convexity ensures a global solution. What is still missing for the real-time implementation is the framework for obtaining a target trajectory XD UD. Again, the problem with the NCM-based feedback control is that it requires the online computation of the target trajectory XD, which is not realistic for systems with limited onboard computational power. So we can approximate the target policy UD by, for example, a neural network, but such a controller can only guarantee that tracking error is bounded by a function that increases exponentially with time in the presence of disturbance and uncertainties. Our approach, based on the ideas of NCM, directly learns a robust control policy of the tube-based motion planner, independently of the target trajectory XD for its real-time implementation. Such a structural difference for incorporating nonlinear motion planning in the NCM framework enables computing U with one neural network evaluation without obtaining XD, while still having the stability and robustness properties of the tube-based planner. As a result, we have optimal deep learning-based feedback control, state estimation, and motion planning frameworks for general nonlinear systems. Also, we finally have most of the formal guarantees we want, except for the adaptation part for online learning. So, as extensions, let's consider the case where the nominal dynamics is not good enough and the disturbance is too large to be treated robustly. This is the final part of the technical details of my work. This is an extension of the NCM control to adaptive control or parametric concern nonlinear systems, where theta is the unknown parameter. Here, we assume that the parametric uncertainty can be separated linearly using the function a of theta. For example, this parameterization includes a deep neural network if we view the weights of the last layer as the uncertain parameter. Anyway, we update the uncertain parameter function a of theta, a hat of theta actually, using what is called adaptive neural contraction metric, ANCM, which is the NCM that also depends on the estimated uncertain parameter a hat. In fact, the ANCM guarantees robustness against external disturbances and learning errors as in the NCM control, and at the same time allows for online learning of the parameter estimate with the real-world information of the real-world environments in order to get improved control performance guarantees adaptively. We also developed the concept of contraction theory-based control for partially unknown dynamical systems. Let's consider systems where the uncertainty can be captured by the function g, and we model it by the spectrally normalized deep neural network. Since g hat indicates the part modeled by the spectrally normalized deep neural network, we can update its hyperparameter using the adaptive online learning technique in the previous slide. Also, since we know that the learning error of the spectrally normalized deep neural network is always bounded, the residual learning error term can be just treated robustly. And this is a final category of the control methods I wanted to talk about, adaptive control and system identification. I had here in this figure. Let me summarize the things I've discussed so far. When the uncertainty can be treated just robustly, the NCM and CB-STEM method will take care of it and gives you a near optimal and robust control policy with the formal guarantees even under the presence of learning errors. If the uncertainty is linearly parametric, then we can use the NCM-based adaptive control for online learning with the same guarantees. If the uncertainty cannot be treated robustly and is non-parametric, then we can model it by the spectrally normalized neural network, deep neural network, and treat each term robustly and adaptively in real time. If the target trajectory and true state are unknown, we can use the extension of the proposed approach to motion planning and state estimation. I see that there are two different ways of using learning-based control here. The methods in the blue frame use learning for replacing heavy online computational load due to the problem complexity and nonlinearity as in method learning, and methods in the yellow frame use them for learning complex and orthogonal scenarios and functions. Now we have all the formal guarantees we wanted to have even in the case of online learning in highly uncertain situations. These formal guarantees are indispensable for realizing the research vision I mentioned at the beginning. From now on, I will briefly talk about the applications of these techniques I talked earlier in this presentation. An interstellar object, ISO, is an astronomical object passing through our solar system on an unbounded hyperbolic trajectory about the Sun. Exploring them has received great scientific attention as one of the few feasible ways to access interstellar materials in situ rather than remotely using telescopes. However, due to their large state uncertainties and high relative velocities, exploring interstellar objects, ISOs, with conventional human-in-the-loop approaches is significantly challenging. The purpose of this joint project with JPL is to investigate the potential of learning-based control, which is one approach to enable first response and autonomous operations for dealing with these challenges. There are a few novel ideas proposed in this mission. For example, we introduced state trajectory imitation loss for neural network training, as in the method of the neural ODE. You can see that by using the loss function, the neural net successfully learns to imitate the state trajectory more precisely at the slight expense of the control effort. The robustness and near optimality guarantees with respect to the MPC solution, which is known to be optimal in terms of the dynamic regret, can be derived again by using the stochastic incremental stability analysis along with the supermartingale analysis. Our method is demonstrated to outperform nonlinear feedback control with a predefined trajectory, LQR with a predefined trajectory, MPC solved with the linearized dynamics for real-time implementation and learning-based MPC. You can see that the errors of our method, Broussard codes, indeed probabilistically stay in the expected error bound indicated by the blue ball here. This is a detailed simulation result performed for 100 ISO candidates, and we can clearly see that our method outperforms the other approaches in terms of the delivery error with sufficiently small control effort smaller than the admissible delta B. This is a video showing the computed spacecraft trajectories for each ISO candidate, which validates that the ISO flyby can be achieved even with the large state uncertainty, vision-based navigation, and high velocity challenges. I validated its performance in this mission also on our thruster-based spacecraft simulator with the interstellar object uncertainty scaled down to this spacecraft simulator system. However, applying such learning-based algorithms to real-world systems always involves unmodeled uncertainties in the dynamics, environment, and control actuation, which could all lead to destabilizing behaviors different from what we learned and what was learned and observed in numerical simulations. Our learning-based approaches have proved to be robust against these uncertainties and help reproduce the numerical simulation results seamlessly in a real-world environment, which can be seen from these experimental results. demonstrated on our thruster-based spacecraft simulator called MSR. This argument is also demonstrated in high conflict distributed and optimal UAV swarm reconfiguration, where the high conflict nature is implied in the naive solution trajectories in this movie. You can see that my method solves such a highly nonlinear optimal motion planning and control problem, but with formal guarantees for its use in safety critical situations. As implied in this movie, my approach indeed works in the real world, with the real world performance consistent with the one in numerical simulations, robustly against uncertainties, thanks to the performance guarantees. Our approach successfully achieves a near optimal swarm reconfiguration of 20 UAVs in real time, even when each UAV is allowed to communicate only in a distributed way. Finally, let me talk about some future directions consistent with the vision of building truly autonomous systems with formal mathematical guarantees. On top of my previous unified framework for general linear systems, which could be conservative in practice, I aim to establish tailor-made theories for each important system of aerospace and robotics, such as systems modeled by a deep neural network. I'm especially interested in highly underactuated nonlinear systems, including UAV swarms with severe rotor failure, and Leo, our bipedal robot with thrusters, which can walk, fly, skateboard, and slackline. We plan to implement our method on an actual spacecraft swarm in orbit in one of my joint projects with NASA JPL called Castor. Next, in poorly known environments and dynamics, we proposed learning-based adaptive control with performance guarantees. This idea is about further using the guarantees to guide online learning of the DNC parameters in feedback for the sake of increasingly optimal performance guarantees, so the agents can have much more radical exploration options even in highly autonomous situations with off-nominal dynamics and environments. Next generation aerospace and robotics missions will involve much more interdisciplinary objectives, performing online optimization with changing definitions of optimality. We can do this by learning the latent information of various tasks offline and learn the part that changes in the real world online on top of the previous methods for the formal guarantees. The vision so far is for building nonlinear control theoretical learning and AI that work anywhere with increasingly optimal performance guarantees and with any changing objectives. However, in extreme situations, sometimes we can only define a very high-level exploration requirement, right? Just find something new and be safe. And the agents have to interpret it mathematically and solve optimization in real time. And I believe this process can be guided also by the control theoretical guarantees, so the agents can use this information back in the decision making still with the guarantees. Also, one limitation of the robust and adaptive control approaches talked earlier is that the safety guarantee depends on the size of the learning error, which could lead to conservative performance guarantees. This idea is about combining the ideas of barrier function-based safety filter designed for second-order control-affine multi-agent nonlinear systems with the ones of robust tube-based safety of contraction theory. Visually speaking, given a learned state trajectory XL, which approximates a global solution XR and is not safe due to its learning error, we apply the safety filter to generate a safe learned trajectory XD in a nominal environment with a nominal dynamics. We then use contraction theory-based robust tracking to guarantee safety even in off-nominal environments with perturbed dynamics with various types of disturbances. We can see the benefits of using the contraction-based robust filter hierarchically when we think about the direction of the forces each filter produces. Since the nominal safety filter makes the safe set stable, it could pull the system over conservatively to the interior of the safe set under the presence of learning errors and disturbances. In contrast, the contraction-based robust filter makes the system incrementally stable and steers the system to a certified trajectory generated by the previous safety filter like this. Because of this distinction, our approach can safely reject large disturbances, learning errors, or uncertainties just with a large safety gain alpha b. This is a brief simulation result demonstrated using nonlinear dynamics of spacecraft simulators with distributed communications. Since the nominal safety filter itself has robustness due to the stability of the safe set, the learned motion planning policy can be augmented to have the safety guarantee when the disturbance is relatively small. It starts to fail for large disturbance, and augmenting it with a conventional CBF approach also results in unnecessarily large control effort due to the over-conservative robustness properties of the safety filter. Our approach, called CART for collision avoidance and robust tracking, indeed guarantees safety while retaining the small control effort even for the large disturbance. Let me also talk about some more ambitious future directions. For example, I aim to use our formal performance guarantees also to guide the design phase of optimal autonomous systems, combining them with system engineering types of ideas. Also, I will extend our approach to situations with much more specific types of uncertainties due to human interactions, system failures, detection, identification, and recovery, or due to adversarial attacks from agents with opposing objectives. Furthermore, I believe that our optimality and performance guarantees can be improved further if we can seamlessly incorporate the knowledge and the ideas of the other field of studies. For example, fluid mechanics, material sciences, structural mechanics, astrodynamics, and so on. For hardware applications, I want to build a hybrid robot consisting of multiple dynamical systems in one platform that work in any environments, using contraction theory-based control to design its universal, robust, and adaptive CNC policy. And I'm open to collaboration, and I'm open to new ideas and feedback. As I mentioned at the beginning, we have a tutorial session on this topic at the IEEE CDC and have a tutorial website on contraction theory for machine learning. And these are the papers cited in this presentation. In summary, the core focus of my research will be nonlinear control theory to build truly autonomous systems with formal mathematical guarantees, as I discussed so far. I also want to have a tight connection between my theories and their performances in practice, where I aim to build aerospace and robotic explorers to turn our imagination into reality in place of humans. Finally, I would like to deeply thank my advisor, Dr. Sunja Chang, for his guidance and advice during my PhD. I truly enjoyed working with him, and I have been so lucky to have him as my advisor. I greatly appreciate the committee members of my PhD defense, Dr. John Doyle, Dr. Richard Murray, Dr. Sergio Pellegrino, and Dr. Michael Watkins, for their invariable assistance in refining my thesis and my research vision. I'd also like to thank my mentors and collaborators at MIT, JPL, and Caltech, especially Dr. Jean-Jacques Slotin and Dr. Fred Hadae. I truly believe that performing exciting research and also pursuing my career in academia, all of them were not possible without their significant help. I'd like to thank the funding agencies for financially supporting my research and my PhD. Of course, my special thanks go to my Caltech friends and my family in Japan and all my friends all over the world. I really appreciate them being there for me, especially during the toughest times. Thank you for your attention.